So today we move into a new chapter. We're going to spend 2 lectures on it. It's chapter 3. What does it deal with? Read the title. One-dimensional. Hey, I like that. Pretty simple instead of 2D or 3D. Just one-dimensional, steady state conduction. Hey, is it anything transient? No, it's all steady state. This seems really trivial. Seems like this would be one of the shortest chapters in the whole book. Guess what? It's not one of the shortest chapters in the whole book. It is when you, after you work through all of it, you realize it is very useful. I mean, it's pretty simple, but it's very useful. So let's take a look. Let's try and uncover it. First of all, they're going to do a plane wall. What do you mean by a plane wall? That's just our rectangular coordinate system just through a slab. Then I highlight that there's some parts of this long chapter that I just skip. I don't emphasize. You can just skip it. So even though I can talk quickly about a porous media, talk about effective conductivity for a porous media because you have a mixture of 2 things there, that's about it. I mean, we don't have homework problems, and I have never had a test problem on it, so you can skim it, and then that's it. Okay. Also, alternative conduction analysis. Oh, I'd love to cover that, but we don't have time, and I have to make some tough choices, and so it's not essential, so we skip that. Then we're going to move into radial systems. So this was all 1D rectangular or Cartesian. Then we have cylindrical and spherical coordinate systems. And then you can see that 3.5 adds something to it. Q dot, heat generation in the energy balance equation. Do it for rectangular, do it for radial systems. Then we're not going to get to it today, so I'm going to leave that for next time. But heat transfer from extended surfaces. Extended surfaces, what? F-I-N-S. Fins. And you see a lot of fins if you start looking around. Engineers have finned a lot of things to promote heat transfer. And this is really important concept for this class. All right, so let's jump into it. Let's have this problem. We have a plane wall of thickness L. It says, hey, didn't we already solve this? Yes, I know we did. And so here's our plane wall, x-coordinate system, 0 to L. And we have a cross-sectional area like that, A. And thermal conductivity, K. Has a specified temperature at x equal to 0 of T1 and specified temperature of T2. So if I plotted the temperature kind of in this direction, maybe this would be T1, and maybe T1 is greater than T2, which is down here. And if it's steady state conduction, no heat generation, we anticipate kind of a boring, flat profile for the temperature distribution. So the first question is for steady state conditions, solve for that temperature distribution. How would you do that? It's a pattern we're going to repeat again and again for this next hour or 2. You get a differential equation. What is that differential equation going to be from? Energy balance, conservation of energy. It doesn't look like it, but think about conservation of energy at a point. That gives us a differential equation. It's called the heat diffusion equation. We were introduced to that last time. And then we look at it and we say, okay, I need additional conditions. For this problem, we'll need 2 boundary conditions, and their specified temperature, and they're given. So what is my governing differential equation, my heat diffusion equation? Last time we had that the Laplacian, wow, I remember all that great math. And write it in 3D and rectangular coordinate system. It was a second derivative of temperature with respect to this first space variable, then the second derivative of temperature with respect to the second space variable y, then the second derivative of temperature with respect to the third space variable z, and then if you had heat generation, which we don't for this problem, and then if it had rho c divided by k, partial of t with respect to time if it was not steady state, if it was transient. But then we say, hey, it is steady state. Hey, there's no heat generation. Hey, it's one-dimensional. So this partial derivative turns into a ordinary derivative And that's the simplest second order differential equation out there. Is there any simpler? No, it can't be. You show me a simpler than that. Isn't this class easy? You bet. And then we have our boundary conditions that the temperature at x equal to 0 is equal to T1, and the temperature at x equal to L is equal to T2. The way to write this would be the derivative with respect to x of something, which is the derivative of the temperature with respect to x. That's the way to write that second derivative. It's like first do this first derivative, and then after that you have something you can do the second derivative. So I would say express it like that, and then do the old separate. So you have the change of the derivative with, and then you have 0 times dx. Kind of a simple separate, right? And now I'm sitting there and I say, this is all 0, but I integrate both sides. Again, that's 0 because you multiply by 0. But when I integrate this, I pick up the dt dx plus C1. What is C1? Where did that fall out of the sky from? What's C1? Constant of integration. All right. Sometimes you can look at your boundary conditions at this point and maybe determine what C1 is. At this point in this problem, nope, let's continue on. But some problems I'll like stop and say, hey, can I determine what C1 is from one of my boundary conditions? If I can, simplifies math a little bit. But now we separate the second time. So we have dt equal to C1 times dx. Hey, now that's not 0 times dx. That's C1 times dx. So when we integrate, we pick up t equal to C1x. Isn't that the integral? Plus another C2, our second constant of integration. Now we have fully busted it out and separated and integrated twice. And so we have our solution with two unknown constants, C1 and C2. So how do we determine those constants? Well, you use your boundary condition. So you have that T1 at x equal to 0 is equal to C1 times 0 plus C2. You know what? I can now find out what C2 is. I conclude that C2 is equal to T1. True or false? True. Yeah, you're right. And then we go to the second boundary condition. And so we say the temperature at x equal to L is equal to T2. So T2 is equal to C1. Hey, I still don't know C1, but it's multiplied by x in my general equation, but I'm substituting x equal to L. And then it's plus C2, but since I already solved for C2, let's put then T1 for C2. Maybe I'm skipping a step or two. You go slower if you need to. But now I could solve for C2. C2 is T2 minus T1 divided by L. I'm done. I have an analytics expression for the temperature distribution. Does it look something like that? Yeah. Oh yeah, I did this C1. I already solved for C2, didn't I? Thank you. Okay, so now what is the rate of heat transfer through the wall? This was the heat equation or the heat diffusion equation. Our other commonly used equation is called Fourier's law. What's Fourier's law? Fourier's law says that Q is equal to minus Ka dt dx. True or false? Yeah, we like that. We already have an analytic solution for it. So you take that analytic solution for the temperature distribution and you evaluate dt dx. What do you get for dt dx? Sometimes you can just look back in the middle of the work. Isn't that C1? And was C1 T2 minus T1 over L? Did you know that dt dx for this problem is the same anywhere x goes from 0 to L? It doesn't change. And so that's just T2 minus T1 divided by L. We have our A, and we have our K with the minus sign. Q is equal to. Somebody says, I don't want that minus sign. Great. Put the K, the A, put T1 minus T2. divided by L. Now, if I look at it the way I'd shown it, if the flow is in this direction, in the positive x direction, if that's the direction of heat transfer, then T1 has to be greater than T2. And that makes sense, that T1 minus T2 is going to be a positive term right there. So there you go. K times A divided by L times the temperature difference across that slab. The higher temperature at 0, the lower temperature T2 at L. Too easy, isn't it? Well, the whole day is like this. Now we come up with the concept of electrical and thermal resistance. We believe at this point you have mastered Ohm's law. Ohm's law. If I have a resistor and I have a flow of current, what symbol do you like to use for current? I. And what is the SI units for current? Amps. So if I have the flow of current through a resistor, I is a symbol, A is for amps in the SI units, and I have a resistor. The resistance is usually quantified by R, or the symbol R for electrical resistance. What SI units for R? Ohms. Funny units. All right. Now there's something that drives the flow of current through that electric resistor. What is it? Voltage. Now this is a little tricky because I learned it's like, okay, we're going to talk about the voltage at this node and the voltage at that node, and they're in units of volts. It's kind of like, come on, V is used so often. So some books use E and E instead of V, and then E is in units of volts. But E stands for electromotive potential or some name like that. It's what drives and pushes the flow of current. Okay? Again, if you look at some books, I'm trying to grasp what exactly some books call it, like electromotive potential. So Ohm's law says that what? E is equal to IR, or E1 minus E2. Isn't it the difference in the voltage that drives it? A lot of times it's just E is equal to IR is equal to IR. You understand that? So let's write it this way. I, because that's what flow is equal to what drives the flow, the difference in the voltage across the resistor, divided by the electric resistance. All right. Well, we have an analogy now with heat transfer. And we're going to have the concept of a thermal resistance. So we had this notion of a slab. We had the high temperature T1 on this side, the low temperature T2 on that side. And what was flowing through the slab? Heat. So what we have is we have the flow of heat, and so we'll draw it like this. We'll have an analog for a thermal resistor. And we'll talk about the temperature at this node and the temperature at that node. And the difference in the temperature drives Q. So, and what is this? Thermal resistance. Okay, so help me a little bit with my units. Well, this would be like in Kelvin or degrees C. It's a temperature difference that drives it. This would be maybe in watts, right? And we're going to get an equation that looks like Q is equal to T1 minus T2 divided by R thermal. Hey, can you tell me what are the SI units for R thermal without doing any more work? What do the units need to be? Yeah, and so you could see that if you want this back to be watts, right? And this is the temperature difference, maybe Kelvin, then I have to have Kelvin over watt for the units to work. So that's a funny unit that resistance has, Kelvin over watt. Now, how are we going to get it? Well, we go back to the equation we just derived. What did we derive? We derived that Q was equal to Ka divided by L times T1 minus T2. Isn't that our equation that we just derived? Can you just stare long enough and figure out what R is? R thermal is equal to, let me get rid of the units here. R thermal is equal to L divided by Ka. Now, sometimes it's like, when you say something like L over Ka, it sounds clumsy, it doesn't sound very helpful. Just memorize something at some point in your life, right? Just L over Ka, commit it to memory. L over Ka, say it 10 times, L over Ka. When I learned ideal gas equation, I'd walk around the bedroom or walk around the living room or somewhere, you know, PV is equal to nRT, PV is equal to nRT, PV is equal to nRT. Here, R is equal to L over Ka. There you go. And then what is L? Thickness, right? Isn't this L? What is K? Thermal conductivity of the material. What is A? The cross-sectional area that the heat is perpendicularly flowing through. All right, very good. So here it is worked out in print, what we just covered. You know, you could do the same thing for our convective resistance. So what did we have? We had a solid wall, we had a convecting fluid, and the convecting fluid had a T infinity for its temperature. The surface temperature was Ts, and there was a convection coefficient H. All right, let's write down our law of cooling. Wasn't it Q is equal to HA, the high surface temperature, if the flow of heat is in that direction? It doesn't have to be, but I like to always think about high surface temperature and colder fluid. Ts, the hot surface, minus T infinity, the cold fluid. Okay, I look at that equation. What is my thermal resistance for the convection? Just doing the same thing we did for conduction. 1 over HA. So from our law of cooling, you can get a convective thermal resistance. 1 over HA. Will it have the same units? What were those units again? Kelvin per watt? Kelvin temperature change per watt of heat flow? Yeah. Sometimes it'll be like degrees C per watt. All you have to do is add 273, right? No, it's a temperature difference. Temperature difference that we're talking about. So 1 degree K is equal to 1 degree C temperature difference. Okay. So there you go. Oh no, this is too easy, but that's our first clicker question for today. All right, let's, how are we going to do? Were you listening? Isn't it temperature change per watt? Yeah, that's what it is. Okay, so there you go. Let's press on. Bookkeeping. Accountants are good bookkeepers. Engineers are good bookkeepers. Welcome to accounting. Right? No, really, that's all it is. And to help us in our bookkeeping so we don't forget something or miss a term, often we use some abstractions, some analogies. And so when we have this thermal resistor analogy, oh no, we could put all kinds of resistors together. Let's say I had a slab of this material A with conductivity A and thickness A. And then I had another slab, material B. Oh, it had a thermal conductivity B and a different thickness, B. And then I had another slab, C, conductivity C, slab thickness. You can see what we're doing. And then you have, you could have some fluid on this side. And it's characterized by some temperature far away. And let's say some convection coefficient. Let's call this T infinity 1 and H1. And over here we could have another fluid. And it's characterized by T infinity 2 and H2. You can get pretty complicated problems. And the way the engineer typically would like to break this down, they say, look, I'm going to introduce a node For each distinct place, I have a temperature. The nodes are like voltages. I have a distinct place I can measure voltage. I have a distinct place I can measure temperature. I could talk about the fluid temperature, T infinity 1. I could talk about this temperature right there. What is that? Some surface temperature exposed to the fluid. What about this temperature? Some interface temperature between A and B where they contact. And then this is the temperature where B and C contact. And maybe this is temperature C surface. If you wanted to, you could introduce names. Temperature A surface, temperature AB contact, temperature BC contact, whatever, you know, is, or you just say temperature 1, temperature 2, temperature 3, just number them. You know, temperature C surface, and then this one is temperature infinity 2. Now, this is temperature infinity 1. We have resistors in between, don't we? And you have to work out what each of those resistors are. This resistor is a 1 over H1A. Now, this gets a little tricky. Sometimes it's easier just to pick or assume A is equal to 1 meter squared, and often that helps us. And then remember, hey, I assumed A was 1 meter squared. So when the final answer, you know, is how many watts were transferred, I say, hey, I picked 1 meter squared, so I'm going to report it as a flux. It's this many watts per meter squared. I don't know if you've already been, you know, challenged with doing that or not, but you should be, and hopefully that made sense. Sometimes it's better. Even though it's a one-dimensional heat transfer, they didn't tell you what A is, and they asked you to calculate the flux. Pick 1 meter squared for A, and then remember that when you report your final answer. Okay, then you're going to have L over Ka, and in that L, we're talking about slab A, material thermal conductivity A. I know I have a lot of A's there, sorry. But then you have L of material B, thermal conductivity material B, cross-sectional area A. Then you have slab thickness, material C, thermal conductivity, material C, slab, you know, area, perpendicular area. And then 1 over the H2A. And then how do you handle numerically when you have these resistors like this that are in series? You just add them up. So the resistance total is equal to that one plus that one plus that one plus that one plus that one. You just add them up. Make sense? This, a couple key concepts. When you have a node, it represents a distinct temperature, just like a distinct voltage. So you need to think, what exactly is that temperature? Now somebody says, what happens if I'm interested in calculating the temperature right in the middle of B? Well, you can introduce a node there and then put, you know, the two resistors where this one will have a thickness L sub B divided by 2 and this will have a thickness L sub B divided by 2. You introduce the node where you want to know the temperature. Sometimes you don't maybe even want to know that interface temperature, but you know that there's a change in the thermal conductivity, so you better put a node at the contact between the two. Solve a few problems, and that'll help. Okay, we have a house, we have 3 layers, we have a wood layer, then we have a insulation, and then we have plaster board, plaster board. All right, and then it's outside. Oh boy, it's cold and windy, and so they give us an H and the T outside, and inside it's hopefully comfortable for us, and there's a convection coefficient on the inside, H on the inside, and temperature on the inside. I think I outlined how to solve this problem enough. If you chase these numbers down, they give you the thicknesses, they give you the thermal conductivities, the L's and the K's, the L's and the K's. You can do the bookkeeping and solve this problem. Here is an Excel sheet. I would, because of accountants, bookkeeping, we don't want to make errors. Sometimes things are tedious. If it's on homework, great, use Excel to check your work, but develop also the skills such that during an exam when you can't use Excel, you can do it correctly as well. But I did the convection on the outside, and degrees C per watt are the units. When I picked one, no, they give us a total area here. Area is 180 meters squared. You get this value, and Excel keeps all those digits. And then for the wood, and then for the insulation, and then for the plaster, and then for the convection on the inside. And then you sum them all up. That's the total. What is the temperature difference between the cold outside, -5, and the warm inside, 25? That delta T is 30 degrees temperature difference. So now, if I know the temperature difference, delta T, I know the R, I can calculate the rate of heat transfer in units of watts, 3820. I think you can do that. In the interest of time, we press forward. Series, parallel. I get them confused all the time. Series is the easier one, isn't it? Parallel, it's like, oh, I could go this way, or I could go this way. It's so electrically, if I have resistor 1 and resistor 2, I can replace those two resistors by a single equivalent system where I have just one resistor, R equivalent. Hey, what was that equation? I think R equivalent is I just take R1 plus R2. That's series. It's not the same equation when I take and combine them. All right, who remembers the, maybe this class isn't hard by itself, but it's the prerequisite not only of all these other classes, but electrical engineering class as well. What do you got? You remember it? Are you holding your hand up? Yeah. So I'd like to do it like this. -1, or you put 1 over R1 plus 1 over R2, and then you reciprocate it. Right? How many people remember? Good, good. You need to remember those things, right? All right? These are the type of things I can ask you on a test with no book. Isn't it fair game? You bet it's fair game. All right. So how about L over Ka? I need my equation sheet, Professor. No, you don't. You can remember 1 over Ha and L over Ka. You can. All right. So there you go. That's how you get it. Now, what do? Not only you have a network that's in series and parallel, but they get combined, and then you have to work through it. And so we will get some systems like that, and here's one. This is a classic. You cannot go through this class without learning how to solve a problem like this. Hands down. No way. Nobody should ever pass you if you can't work a problem like this. Did I emphasize the importance of this? Because if you go past this guy, oh yeah, I got an A, my TOEFL's class heat transfer. Hey, let's talk about flow of heat through a wall of a house. Oh, that's too complicated. Oh, no. So we have a composite wall of a house. You could see, what do they call this thing? A stud, right? And I don't know why they call things the things they call them. It's just what a stud is called. Sometimes I remember I didn't know what a stud was. Somebody said, go there and pick up them studs and bring one. I said, whoa, what's that? Am I looking for some, metal thing about 3.5 inches long and maybe in a big bucket? Is that what a stud is? No, it's a piece of wood, right? About 8 foot long or whatever it is. Not 8 foot. How tall are they? 96 inches? How long is a stud? It is 8 foot? About 8 foot long. And then they have, like 2x4. You pay for the 2 inches and you pay for the 4 inches, but you get 3.5 inches and 1.5 inches if you actually measure them. And then I think they actually dock them a little bit, don't they? For framing, they actually don't give you a full 8 foot because they know that the header plates and blah, 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 the bottom plate. So they're a little bit less than 8 foot. But hey, I wasn't thinking about that when I prepared this lecture, so let's just move on. So, but I'm telling you, some words are confusing when you first see it. Like, what's that? A stud. Really? All right. Now, a lot of them up north, they're 2 inches by 6 inches. But that's just because up north they have long winters and they need more insulation in the walls. It's cost effective to build with a 2x6. Everything around here is a 2x4, unless they've moved. Anybody know if they've built a house 2x6 wall around here? I've never seen it. But up north it's extremely common, 2x6. Okay. Now you're going to have a stud and then another stud, and there will be a distance between studs. Right? So what are they? 16 inch on center? 16 inch on center typical? Okay, we haven't moved completely to metric, so we're talking inches still. And then you have outside wood sheathing and then the wall board. So what I would do is I would think about, you have a flow path that goes through the wood siding, then it can go through the stud or through the insulation. So you have a choice there. Okay, for this problem, they tell you what is that area of the wall. It's 2.5 meters high by 6.5 meters wide. That area is 16.25. So the area, 16.25 meters squared. So the whole wood is 16.25. The whole wall board is 16.25. But if you have 10 studs, you have to figure out what is the area that it's flowing through the 10 studs. All right? And so this thickness right here of the stud, what is it up here? It's they're on 0.65 meter centers. That's that distance from center to center of the stud. It's 40 millimeter by 130 millimeter. Okay, they show me right there. It's 40 millimeter thick, isn't it? So what I need to do is to get the area of the stud it's the 10 of them, 10 studs, and they're both, or each one of them is 0.040 meter thick or for the area. And then how tall is it? It's 2.5 meters high. That will be the total area to go to the stud. And then what about the area for the insulation? Well, that's going to be, the sum of this area and that area. And the one way to think of it is it's the total 16.25 meters squared, the total area of the wall, subtract off the stud area. Yes, sir.
What was the 130?
That's this thickness right here. That's our L in the direction of heat flow. Yeah. So it takes a while just to get the areas right on these. I know it's geometry, but you have to get the area right. So hopefully you understood, where did this 16.25 come from? 2.5 times 6.5. Where do I get the area of the stud? Let me see, the numeric value for the area of the stud is 1, actually. 1 meter squared. Take 10.04 times 2.5. So it makes it simple, the math simple. And so the area perpendicular for the flow of heat through the insulation throughout the wall is a total of 15.25 meters squared. And then what's the area for the flow through the wallboard? Well, the same as what it was through the wood siding. So now what we do is we set up a resistor. It's got to go through the wood siding, then it can go either through the, let me draw that again, through the insulation or through the stud, and then it's going to go through the wallboard. Wallboard, stud, insulation, and then this is siding. So I have to combine the insulation and stud to one equivalent resistance. The equivalent. How am I going to do that? Well, they're in parallel. And once I do that, then I have the siding and I have the wallboard, and I combine all those into one resistor for the total wall. And guess how I do that? Well, that's series. That's easy. And then the total thermal resistance for the wall. Hey, what's the units going to be on my answer? Total thermal resistance for the wall. Yeah, degrees C per watt or Kelvin per watt. And there you go. So this is, again, tedious bookkeeping. On the next sheet, I have a piece, I show it in Excel format to lay it out. Let me do that. So I just put in what is my H and width of the wall. I multiply those together in Excel. There's my total area. And then what's my distance center to center for the stud that was given in the problem statement? 0.65. How many studs do I get? Well, you take center to center and you divide the width of the wall, you'll get 10. See that? You get 10 studs. And then down here, you say, okay, probably the hardest part's finding these thermal conductivities for the siding and then the stud, then insulation, the wallboard. Well, I got off track a little bit, but they're like this. Most of them, 3 of the 4, are in table A3. They are in table A3, and that takes some time to go find them. But just pay attention to the wording in the problem. It's like up here, it's like hardboard siding. Then the next one, hardwood studs. Do we have a lot of hardwood studs around? No, 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 no. There's no oak studs in the houses that, you know, they're being built now. They're all this, they're fir, aren't they? Isn't it a fir? It's not a pine even. It's a fir tree. You know, anyway, but anyway, then glass fiber insulation. It's paper faced with this weight. How many kilograms per cubic meter? When you get to the table, then you, oh, there it is. Now I understand. And then this is the gypsum, and there's a vermiculite wallboard, and that's also in a table, so you can find them. So just table A4 for the insulation. You have to get these 2 resistors, and then I combine them. One extra step right there. What is that? So I can now sum the 3 in series. So the parallel and then series, and then there's the sum. Then you can go back and do a little diagnostic. What is the contribution of the siding to the overall percent? You know, what fraction is it, or what percent of the resistance to heat transfer does the siding? Siding is not to resist the heat transfer. It's like a whopping 3%. And then wallboard on the inside. Again, that's not for resisting heat transfer. It's a whopping 2%. When you have that stud insulation combination, where most of the wall is insulation between structural supports of studs, there you go, 95%. Somebody says, why don't, if you want to build a super insulated house, sure, put a 2x6, you get more insulation, right? That's why they put a 2x6. Somebody says, well, why don't they do a wall like this and put a 2x4 and then a 2x4, and then I don't have that thermal pathway through a continuous stud. Yeah, go get a contractor with the workers to actually build a wall like that. I'm sure it'd be great. Okay. Now we move on to contact resistance. You have 2 materials. You put them in contact. You know what? That can offer a significant resistance to heat transfer, especially if they have if they're rough materials and they're very hard materials, not very compliant, and you don't have a lot of pressure pushing them together. Now, if they're softer materials, then when you push them together and you put a lot of normal force there, then the little peaks and valleys blend in. But what you'll do if you zoom in, you see that you have the contacts are in certain spots, and then you have a lot of void places. Okay? So a lot of this depends on what is my pressure pushing them together, how soft or hard the materials are, and then also what's my fluid, that's what they call the interstitial fluid that's in there. Anybody work with electronics? You have that little thermal grease. Sometimes they call it like silver oxides or whatever. And then you just put a thin layer before you put your heat sink on the CPU. And then they clamp it down, little springs, click, click. Okay, well, you know, they have all kinds of high conductivity names for those, but they're usually better than air, but they're really not great. I mean, it's better if you could get a great contact. So, but this is a real problem. So the book talks about a contact resistance. Oh, I like that. And they have a T and a comma C. Now, we use R for resistance. I'm not certain what the subscript T is for. What do you think? Thermal. That makes sense. Comma. What do you think this C is for? Contact. So far, so good. Actually, it's not that bad. And then they put this double prime up there. Let's not talk about the double prime for a minute. Let's go over here and say it's a TA minus TB divided by Q in the X direction double prime. All right. Okay, now I'm used to seeing Ohm's law written something like this. I have what is a flow is equal to a temperature difference, TA minus TB, divided by resistance and now thermal contact. So it's like they threw this one up here and they put that one down there, right? Does that make sense? But then they wanted to say we're going to talk about, instead of the flow of heat in watts, we want to talk about heat flux. So here's my contact to the two materials, and there's a temperature on the A side and a temperature on the B side. Really, there's a temperature difference right there at that contact. So A and B are close together, but they're different because of the contact resistance. And the flow of heat is in this direction, Q, or they'll talk about the heat flux. The heat flux, fine, it's per unit area. Okay, as soon as I did that, let me do this. Let me write this equation, modify this one. So let's switch locations, put RTC there, put the Q down here. Now, in order to go from Q to Q double prime, do I take and I put 1 over A like that? Do I multiply like that? Yeah, which means that I need to do that both in the numerator and the denominator. Or I'll do it like this. Won't it be like that? Okay, mathematically, when I put the A, is that okay? But you shouldn't assume everything I write down on the up here is correct. You should check it. We already found one error. Thank you for those that found that error earlier, right? But is this right or not? We got 10, 12, 13 people say it's right. Okay. So now I can replace this becomes Q per unit area. This is TA minus TB. I don't know why the authors of the book say, oh, RTC, if I multiply by an area, I'll replace that by R double prime TC. Hold it. The first thing I look at, if I have Q and I divide by A, that's Q per unit area. If I have R and I divide by A, that's R double prime. That makes sense. But no, this book says R double prime is going to be R times A for this problem, for this thing. So anyway, it's confusing notation. I point that out. It's not what you would expect. Okay, let's go back and look at what are your SI units for R, thermal contact. Degrees C per watt or Kelvin per watt, is it not? If I multiply by A, don't I get meters squared, degrees C per watt? That is the unit of this term, R double prime TC. But if somebody said, here is what you would expect the definition to be, you would expect to have unit of degrees C per watt. I divide by A, meters squared. I would expect R double prime. If nobody told me what it was, I would expect it to be degrees C per watt meter squared. See that? Why it's confusing? I would have preferred the book, and a lot of the literature uses contact conductance, but this book really doesn't. that I'm introducing you, if you were in a different book, you would maybe see contact conductance in terms of H. It's just like a convection coefficient, H. But they put a subscript C for contact, and they call it contact conductance H. Okay, but this is not in this book. This is in the book. So you go to this table. We want to spend a little time on table 3.1. We have the thermal contact resistance for part A. Where is part A? Right here. That's part A. And then for part B, that's over here. Part B. But look at metallic interfaces under vacuum conditions. So forget about air or silver, paste, whatever. It's just vacuum condition. Could you ever have two metallic surfaces in contact in vacuum conditions? Somebody I see has a NASA shirt on or hat. You bet, man. You go outside and fly halfway to the moon, and most of the trip is the vacuum. And if you got two things that you bolted together and there's heat transfer, guess what? You got two metals with vacuum conditions for the interstitial fluid. Now, what they're showing you is that they have the contact pressures changing. Which one's higher? This is the high contact pressure. What happens if I have stainless steel in contact? Notice that the higher pressure, doesn't this go down? Higher contact pressure, pushing those little mountains together, making better contact. Less thermal resistance. Same for aluminum, etc. Now let's take a look at here. They have, for B, they just focus on aluminum interface with 10 micron surface roughness. Now they didn't tell us what this aluminum surface roughness is down here in these parts. They really should have, but they didn't. Not that I saw. But here it is. So there's a surface roughness for part B. And they give us this pressure. So one pressure, not high and low, normal force pushing the surfaces together. And they say, look, if you have air, helium, hydrogen, silicon oil, or glycerin, which one gives you a high thermal resistance? Remember, this is a contact thermal resistance. Air, it's a poor conductor. Hydrogen, helium, remember those? Monoatomic ideal gases, high conductivity, better. But then if you put in some liquids, oil, they have better conductivity often. And there you go. So you can see the trend there. Now, this is a little confusing because they've got this 10 to the 5th Newton per meter squared. Then they got these pressure units or normal stresses here and here. So I have a clicker question for you. Which statement is true? I talk about 100 kilonewton per meter squared. That was part A of the table. Or I talk about 10 to the 5th newtons per meter squared. Just compare them. Is it less than, equal to, or greater than? Answer A, B, or C. Everybody in? Let's stop. All right. I still am always confused why this one's not 100%. They're out of the room? They're out of the room. Even if their body is physically here, they're out of the room. Why did I even ask that question? Again, take a look at how the textbook has it. They have, this is the pressure there for B, but then over here they have this. Some students may think, oh, they're different. Are they different? What's a kilo mean? And I'm going to say that this section we just finished, this is the first part of this chapter 3. We need to move into now the radial systems. Okay? So I'm going to jump over to another slide. Let's jump into now the radial system. What do you mean by radial? Cylindrical and spherical coordinate systems. So up here, the whole thing was the second derivative of temperature with respect to the x direction equal to 0. What is it down here for the cylindrical? 1 over r derivative with respect to r of r derivative of temperature with respect to r. That's equal to 0. What about for the spherical? 1 over r squared, derivative with respect to r of r squared, derivative of temperature with respect to r equal to 0. That's it. So we just redo everything, but now we have a wall in a cylindrical coordinate system, like a layer of insulation on a pipe, or a layer of insulation on a sphere. That's it. All right. So this would be a pipe. Maybe the inside is hot, the outside layer, is exposed to convective fluid, and a good question is what's the resistance associated with that layer of insulation around a pipe? So what do? You have a cylindrical shell of length L, has a thermal conductivity K, has specified temperature at T1 at R1. So this is at R1, you have a temperature T1, and at an outer radius R2, you have a temperature T2. Can you get the temperature profile, the radial temperature distribution? Can you get temperature as a function of R? Isn't this our differential equation? Isn't this my boundary conditions? What did we do here? We did our first separate, then integrate. We have a first constant of integration. What do we do here? We just manipulate, then we do a separate and integrate, and we have our second constant of integration with the natural log of r in there. You apply your boundary condition 1, boundary condition 2. You find C1 and C2. They're not pretty. You then express your total temperature as a function of r. You apply what law? Fourier's law to get an expression for Q, because you have an analytic expression for T. Now you can get that derivative. There it is. You do a little simplification. Then you do some name calling, because it's like the flow of heat driven by a temperature difference, 1 over thermal resistance, the thermal resistance natural log of the outer radius divided by the inner radius divided by 2 pi KL. You say it 10 times. Natural log R2 over R1 divided by 2 pi KL. And before you know it, you have it memorized. Now to rederive it, that's this work that's summarized on this page. So the profile has this shape like this. See it? T1 and T2. It's not straight. It has some concave upward shape to it, given by that analytic solution, that natural log term right there of R. All right. Feel good? Keep going. Do it for a spherical. What changed? All that changed was you had the 1 over r squared derivative of r squared times dt dr. So that just cancels because you multiply it both sides and the other side is 0. And then separate, integrate twice, get a general solution, apply your boundary conditions to get C1 and C2, get an overall distribution profile equation, apply Fourier's law, do some name calling, and there's your resistance. 1 over R1 minus 1 over R2 divided by 4 pi K. Look good? Once you have those, you can solve a lot of problems. Here's a table that summarizes it straight in the book. So the heat equation, cylindrical, spherical. Then you have that temperature profile or temperature distribution. The natural log of R shows up here. Then you have the R over here. The heat flux, the heat rate, Q, and then the thermal resistance, L over Ka, natural log R2 over R1, 2 pi KL, 1 over R1 minus 1 over R2, 4 pi K. Good summary. And then you solve a bunch of problems. Let me do this. Let me give you either, I'm going to have to give you time to solve that one or another problem. Do you want to spend some time on this one? We have hot water flow through a 3 centimeter diameter thin-walled copper pipe. When you say thin-walled copper pipe, the wall of the pipe is thin, the copper has high thermal conductivity, should you have a difference between the temperature on the inside and outside wall of the pipe, or should you just have one temperature for the copper pipe? One temperature for the copper pipe. Basically, you neglect the thermal resistance through the wall of the copper pipe. Commonly done. It's wrapped with 2 centimeters of insulation. Now, does that mean that if I have the center here, and this is my radius 1, is this my layer of insulation? Is that 2 centimeters? So that when I swing this around, that I also have 2 centimeters on this side as well? So if I want to go, the inner layer of the insulation is R1, the outer layer of the insulation, maybe I should put the value down for R1. If the diameter is 3 centimeters, what is R1? 1.5, thank you very much, let me put it, R1 is 1.5 centimeters. Okay, now what is R2, the outer layer of the insulation, that radius for the outer layer of the insulation? This is hard, this is where a lot of students will mess up. You've got to add 2 and 1.5. And so it becomes, 3. 3.5, isn't it? Perfect, thank you very much. So what's the outer diameter of the insulation? You don't need it, but what is the outer diameter of insulation? It's 5 centimeters. True or false? False. What is it? 7. There you go. See, I can't trip you up. That's pretty good. So the water is flowing through here. It's got a temperature infinity of the water of 80 degrees C and a convection coefficient H on the inside given. And it's surrounded by air on the outside. So way over here is air. And its temperature infinity on the outside, let's call 2, is 25 degrees C, maybe T infinity 1 down here, and then H1. And then H2 is 20 watts per meter squared degree C. Calculate the rate of heat transfer per unit length of the pipe. So I'm going to pause and let you work on this for a minute. How are you going to set that up? How are you going to solve it? And I'm going to take this opportunity to... Well, let's take a look. Did you get a resistor? Natural log R2 over R1, 2 pi KL. Did you put numbers in? Maybe get something really, really small. Guess what? All the thermal resistance, 92% of the overall thermal resistance of those resistors in series is dominated by that insulation, as it should be. You sum them up, that's your total. In this, what I typically do is I like to pick a length of 1 meter. Then know, hey, everything I'm doing per meter, so that if I want to express it like the final answer is, instead of saying 18.8 watts, I could say, oh yeah, it was per 1 meter, 18.8 watts per meter. Now we need to move into this section. What changes? Thermal energy generation. What's added? Well, you go back to the plane wall, you have the second space derivative of temperature, and you add Q dot divided by K. That's it. And then you're going to do the same thing for the radial systems. A lot of times a radial system, they'll have R goes between 0 and R naught, meaning a solid rod with heat generation in it. The classic example of that, this is be the center line going down, is a nuclear fuel rod. What do you mean nuclear fuel rod? I know they have them little pellets, but basically the fissioning happens throughout the rod or throughout that pellet, and the heat has to be conducted to get to the fluid that's flowing on the outside of the rod. And so there's a good example of cylindrical solid rod, radius R naught, with Q dot heat generation inside. What's my governing differential equation? 1 over R, derivative with respect to R of R, derivative temperature with respect to R, plus Q dot divided by K is equal to 0. Solve for the temperature distribution. All right. So the same thing with the cylindrical. Let's press forward on this. So you just got to start doing it. So if I have a wall of thickness 2L, usually we put at the center line or the middle point, that's where X is equal to 0, and then L, and then this is minus L, hence the thickness is 2L. Conductivity K, uniform heat generation, Q dot. The temperature at negative L is TS. Maybe we use this direction for plotting T. And over here is TS, both at plus L as well as negative L. What do you think the profile is going to look like? It's going to look like that. Where's the maximum going to be? Right in the middle. It's symmetrical. There's nothing to be not symmetric. It's going to be symmetric. So how do I find that temperature distribution? You have the governing differential equation. So we have the second derivative of space plus, well, put the equal to minus Q dot divided by K. Separate, integrate, two constants, supply your boundary conditions. Because it is symmetric, somebody could say, I'm going to use boundary condition number 1 to be the rate of change of temperature with respect to X at X equal to 0 is 0. It's got to have a slope of 0 at X equal to 0. And so you could say, I'm just going to focus on solving, between 0 and L. And I know it's symmetrical. And I'm going to use that boundary condition. As well as another boundary condition, number 2, that the temperature at L is equal to TS. Either way. But you have to be able to do that. Guess what you're going to get? Quadratic. It'll just be a quadratic. So this is the equation. Here I even just used those two boundary conditions at negative L and positive L. You get your C1 and C2. You see that, it looks like AX squared plus BX plus C is equal to T, where this is my A coefficient, B and C coefficient. And then you just have a couple questions, like little reminder, what do you know about the quadratic equation? But let me do it anyway. So the quadratic equation, what are the roots? You got this memorized. I've seen it on a couple tattoos. Negative B plus or minus square root of B squared minus 4AC divided by what? 2A. That's a long equation to memorize. You know what? I think this part of the equation is really significant. Do you know why? Because that tells you where the min or the max is, if it's concave up or concave down. Negative B over 2A. It's really kind of important. Interesting, isn't it? So there's your quick review. So where you're going to get the min or where you're going to get the max is just negative B over 2A. And then you have this push out and push over. That's that plus or minus the square root of B squared over minus 4AC, square root of that. Hopefully that's a quick review because, yes, our temperature distribution is simply a quadratic. It is easy. Then what's the slope at the min or max? Guess what? 0. Yeah, its slope is 0. So if somebody says, where's your maximum temperature? It's at this. If you take a look at it for this problem, if T1 is equal to T2, meaning on this side and that side they have the same temperature, T1 and T2 are the same, guess what happens to B? The coefficient B in the quadratic equation? 0. Guess where the max is? At the middle. Not too surprising. A wall of thickness 2L and conductivity K has a thermal uniform heat generation Q dot. Temperature is TS at negative L, and at positive L it's also TS. How will the temperature profile change if Q dot is increased. Maybe it was 5 watts per meter cubed, and now they boost it to 50 watts per meter cubed. Increase Q dot. What is the change in our profile? Well, are we done? Or do you need more time? Yes, sir.
I have a question about precisely. How do we know that it's going to be symmetric about the performance wall? Is that always the
It won't be if the two temperatures are not the same. But if they're the same, they'll be the same. It'll be symmetric. Okay. I'm going to go ahead and stop. And we show the results. Oh boy, maybe I didn't give you enough time to read, or maybe you're just tired of reading. Which one is it? The maximum temperature will go up, won't it? Basically, this is the right answer. E, the increase in the maximum temperature, which is at location X. If I come back to this quadratic equation, I see that the maximum temperature is at negative B over 2A. For T1 and T2, that's going to be 0 right there. B is 0. And so I have this term goes out. And so the temperature is equal to AX squared plus a constant. Okay. At X equal to 0, this is just the maximum. So the maximum temperature is going to be the average of the two surfaces, which they're the same, so it's just TS. This is going to be TS plus Q dot L squared divided by 2K. That's T max. So as it goes up, the profile goes up, and the max temperature goes up. I'm sorry? Well, this is TS, you're right. T1 is T2 for this problem, TS. So hopefully that made sense. You're going to have a higher maximum temperature, but the location doesn't change. The TS stays the same. You just pick up an increase where the max temperature goes up at X equal to 0. Okay. Maybe that wasn't so good. Let's try another one. We have a wall thickness 2L. Conductivity K has a uniform heat generation. What does the heat flux do as Q dot goes up? Well, think about it. It's like this side is insulated, so everything generated in here has to be pushed out over this surface right there. So the heat flux at X equal to plus L goes up when Q dot goes up. All right, I can see I ran out of time. Here are plots where T1 is not equal to T2. And you can see what happens. Does the maximum stay in the middle, or does it shift over? It shifts over toward the higher side, higher temperature side. All right. All of that works out of our analytic expression for our quadratic temperature profile. Radial systems, I'm going to have to probably talk about this some more next time. I see I'm out of time. Thank you for your attention. Please solve problems. That's the way to learn. And pick up your homework down here. Thank you.